Good day class, welcome to lecture number 4. Today we will talk about problems with sampling and spatial resolution, and then we will continue our talk by talking about the image enhancement. And this image enhancement topic is quite big, so we will spend a couple of lectures on talking about this image enhancement. Now, the problem that we have in the sampling and spatial resolution is something which is called the spatial aliasing problem. If you remember from lecture number 2, I referred to that problem. Now we will talk slightly more in details of this spatial aliasing. Spatial aliasing is insufficient sampling of data along the space axis, which occurs because of the insufficient spatial resolution of the accurate image. Now, it is recommended, if you remember, to sample the image at a rate which is close to the identical sampling rate. Remember the Nyquist theorem, which was saying that the minimum sampling frequency should be twice higher than the maximum amount of frequency that we have inside an image or in the signal. So images obtained with sampling distances larger than those established by this rate suffers from undersampling. In other words, you know that we have these cameras, and the cameras have fixed sampling rate. So if inside the image that we have very high frequencies which are not satisfying the Nyquist rate, then we are undersampling these images or frames or part of the image. And this will cause something which is called a spatial aliasing. Now, let's define something which is called the critical sampling distance. It is the sampling distance corresponding to the Nyquist rate. So, in statistics, signal processing and related discipline, aliasing is an effect that causes different continuous signals to become indistinguishable when it's sampled. In other words, we are doing the sampling, but from the sampled signal we cannot retrieve the original signal. When this happens, the original signal, as I said, cannot be uniquely reconstructed from the sampled signal. We can assign more than one signal to that, as you can see in the slides, in the one dimension, and also in the two-dimensional image. You can see what is the undersampling image look like. Can you see the patterns which has been created in there? Now, let's see how we can solve this spatial aliasing problem. Spatial aliasing problems can be solved by something which is called anti-aliasing, and it refers to the low-pass filtering. So anti-aliasing refers to the low-pass filters applied to an image before it is downsampled to avoid aliasing artifacts. So while we are using the low-pass filter, we will talk about low-pass filter, high-pass filters, and different type of filters later, because low-pass filter will guarantee that we don't pass some of the high frequencies. In other words, the maximum frequency that we pass will be set by our function, by our filter. So we can always set that cutoff frequency to be half of the maximum sampling rate that we have in our camera. So the filter removes high frequencies contending from the original image, which means that it is reducing the bandwidth, and therefore then we will have a lower sampling density in the downsampled in downscaled image. And this one will help us when we are recording with the camera. We will have no aliasing. And here in this slide you can see the image with aliasing problem, and if we are applying the low pass filter and then we do the sampling, you see now we don't have the aliasing effect. Okay, now This aliasing happens usually in something which says that we have Moire patterns. Moire patterns are the type of patterns that we have lots of repetitive patterns, like lots of parallel lines, which means that we have lots of high frequencies. And usually we need to apply the low pass filter before we are doing the sampling. If you remember, I said that when we want to make video, when we want to go to TV and have interview, they ask us not to have lots of shirts with lots of strips, because it will cause them aliasing. Now, as I told you, today we will start to talk about image enhancement. So let's define what is image enhancement. Image enhancement is the process that improves the quality of the image for a specific application. So based on our application, we are doing some enhancement. Now, this image enhancement can happen in two ways in general: a spatial domain method and frequency domain method. And we will start with the spatial domain method. We will talk about it in a couple of lectures, and then we will talk about the frequency domain method. In the spatial domain method, the term spatial domain refers to the 2D image plan, and the approaches manipulate the pixel of the given image for enhancement. So what we do, the function that we define will work on the pixels directly. So if we do something, the outcome will be a new pixel value. We don't need to do any transfer and inverse of the transfer. But in the frequency domain method, this method is in the frequency domain and manipulate the pixels after being transformed into the frequency domain by using the Fourier transform of the given image. So in the frequency domain method, we have the image, we transfer it into the frequency domain by using the Fourier representation, and then we enhance in frequency domain. And then in order to see what is the outcome, we have to do the inverse of the Fourier transform, and we get back to the spatial domain and look at the image. Now, spatial domain methods are the procedure that operates directly on pixels, as I said. And a process in the spatial domain can be denoted as a transform on the image, and the outcome is another image. So the input and the output are images. And as you can see the general formula in the slide, the T that we use is the operator or the transformation function, which works on F and give us the image G, and it will affect on the pixel value of X and Y and its neighborhood. Now, a neighborhood over or about the pixel X and Y uses a square rectangle subimage which is centered at X and Y. So we have to define what we mean by this neighborhood. Here in this slide, you can see a 3 by 3 mask or neighborhood. So a 3 by 3 mask at X and Y means that the center of this mask, as you can see, is at point X and Y, and we have 8 other pixels around it. So the center of the rectangle sub-image is moved from the left top of the image to the right bottom of the image, and we visit all the pixels, and it will do whatever the duty of the mask is. So G, X and Y is calculated, and the output image is formed as each pixel is processed. Now, if a 1 by 1 neighborhood is used for the transformation function, then the function is called a gray level transform function. So let's talk about the point processing, which refers to the processing technique where the enhancement at any point in an image depends only on the gray level at that point. So it means that we want to know what is the value at this specific pixel value. So the future value will depend only on this value alone. Now, then what we have mask processing, as I said. Mask, we sometimes refer it as a filter, kernel, template, window. So if I interchange between the words, you have to know that they are all the same. So mask is a two-dimensional array, let's say 3 by 3, 5 by 5, defined around a pixel where the value of the mask coefficients determine the nature of the process. We will see few famous masks, and based on the weight and values that we have in these masks, we will see that we call them different names because they will do different duties. Image enhancement method using mask approach is called mask processing or filtering. And now you see we are using the word filtering, and we do the filtering in the spatial domain. Later we will see how to do the filtering in frequency domain. Now, one of the first things that we will do in image enhancement is image illumination enhancement. And basically, we will learn how to do the contrast enhancement. Contrast is the difference in visual properties making an object or image distinguishable from other objects and the background. In visual perception, contrast is determined by the difference in the color and brightness of the object with other objects in the same field of the view. If an image is dark or bright, the information may be lost in those areas. So the problem is how to minimize the loss of the information. So in the next lecture, you will see that we will start to talk about image enhancement in the spatial domain. We will start to focus on contrast enhancement. I hope that you will enjoy this lecture and see you in lecture number 5.